Okay, so we're talking about here questions 19, 20 from the homework, and ultimately the big issue comes in the last part of these questions. I'll ask about the range. Okay, let's go through real quick because I think it is beneficial to at least find all of the components to come up with this graph. We've got the question of whether we have holes or not. We have our vertical asymptotes. Horizontal asymptotes, or if you think about the other couple questions in your after 1920, so I'm talking about slant asymptotes. We'll get into that today. X-intercept, Y-intercept. We should also add in here whether we cross the horizontal asymptote. If I look at the original function, x of x, I need to factor that thing, so it's going to factor to, obviously the top is still 9, but the bottom is going to be, what, x plus 1, x minus 9, okay? So the question is, do I have any holes in, or what we call point discontinuities? That's where we have common factors, right? Okay, things that can cancel, we don't have that, so we have no holes, okay? Vertical asymptotes are where you divide by 0, correct? So what x values are going to give you vertical asymptotes? -1 and 5 and 9, right? So those two equations, x equals -1, x equals 5 and 9 would be my vertical asymptote. Now my horizontal asymptote or my slant asymptote, I'm going to look at the leading terms. 9 divided by x squared. 9 divided by x squared, okay? Because I'm left with a variable, nothing cancels out, I'm left with a variable, I have to ask myself, what happens? What is the horizontal asymptote's purpose to tell us in behavior? In behavior is when x values get really, really, really big, right? So I plug in a really, really big number for x. I square it, get an even bigger number, divide 9 by it. What's that get to? Gets to 0, right? So y equals 0 is my horizontal asymptote, okay? I want to know, do I cross it? Okay? So what we end up doing is we set this original rational equation equal to 0 now, okay? You would first multiply both sides by the LCD, right? Or cross multiply if you prefer that route. And isn't that going to essentially make this down here on the bottom vanish? And now you're left with y equals 9. Does that make sense? I'm sorry, 0 equals 9. 0 equals 9. Does that make sense? No. Okay? That's a false statement. So when I get a false statement, that means I do not cross. Okay? We've learned back to Fisher's equations in Algebra 1 when you had two lines that ended up being parallel. If you use a system with them or set them equal to each other, you ended up getting an argument that was like 0 equals 9. It gave you the fact that there is no location of an intercept, okay, or intersection. So now I go x-intercept. Okay, now think about this. Think about this. If, and this is going to allow you to do your work a little bit faster sometimes, and this is the math aspect. Okay? I think a lot of the things that we're doing here is more arithmetic, more algebraic, analytical stuff that you can kind of maybe sometimes want to get in the groove of being robotic and you don't think about what you're really doing or what you've done and how it relates to other things. Okay? Those relationships are the math. Okay? You found a horizontal asymptote at y equals 0. What's another word for y equals 0? X-axis. Okay? You just figured out that you do not cross y equals 0. So you do not cross the x-axis. So if you do not cross the x-axis, can I just skip this part? Okay? I have no x-intercept. That's something I want you guys to start realizing. It's just a small kind of situation right now where you can use your understanding or your relationships between the math that you found and the math that you're going to do to help you be efficient. But that kind of thing happens over and over and over again as you move through the rest of mathematics. Being able to recognize how one idea or concept impacts or influences something else. Okay? Those relationships, those implications of one concept to another, that's the math that I'm interested in you guys understanding. Okay? Y-intercept, be a comparison of those things, right? Okay, because y-intercept is when x is 0, so that's going to go away. That's going to go away. That's with 9 over negative 9, so y-intercept of 0, negative 1, right? Okay, so you can see over here, obviously I found the right graph in Web of Science to cut that out. All the things that we found on the left-hand side mimics the picture, right? Okay, now, the part that they ask you that people are struggling with is the domain and range. And it's not the domain that they're struggling with, because when they see the domain, we've done a lot of that. We understand that it's just the places you can't have an x value, right? The places that you could not divide by 0. So we go negative infinity up to negative 1, union then negative 1 up to 9, union then 9 to infinity. That's my domain. The range is where we're getting kind of hung up. Okay? Remember the range, you start with a horizontal line down the bottom, right? And you start sliding that thing up. What would be the first y value that I come across? Negative infinity. Okay? Now I'm going to get up here. Okay? Are there values between right there that I'm going to have y values for? No. Okay? So that's an issue. It looks like my last y value is where my cursor is, right? Do you agree with that? Now I'm going to, when we talk about range, there's not a really nice way right now to find the range other than to use our original function and to evaluate. Okay? So at what x value do you think my cursor is sitting at right now? An x value of 4, right? Okay? So should I be able to, if that x value is 4, should I be able to plug that 4 in up here? And when I plug 4 in up here, I get 9 over, that's 5, and negative 5. So I get 9 over negative 0.5, and negative 0.36. Okay? Now, here's the thing. They ask you to go through and round to the nearest tenth place. So what's the nearest tenth place? It's negative 0.36. Negative 0.4, okay? So negative 0.4 would be what I'm looking for right here. Okay? Now here's the thing that I think is weird. Negative 0.4, okay, so like right, it's just the graph is zoomed out so far. Like negative 0.36 would be about right there, right? Negative 0.4 is going to be under it, right? Would negative 0.4 be included or excluded? It'd be included, okay? Now, I don't like that because what we've really done, when we were around at that negative 0.36, what we've really done here, guys, is we have excluded values between negative 0.4 and negative 0.36 that are actually part of my range. Does that make sense? But they do that rounding because the rounding, I don't know how to explain it the best. We'll see in the next example, I think maybe the reason that they ask you to round to the 10th place because of your choice of what you're going to evaluate your curve at might be up to you, I guess, okay? So we'll see it in the next example. But we won't include that, okay? I wish they would just say, because this one can be done this way, at negative 0.36 terminates, just let that be my largest y value. Does that make sense? Okay? I guess the main reason for this is, if I plug in, what happens if I plug in 5 here? Go 9 over, what would be 6 times 4, right? Okay? So we get 9 over 24. Well, 9 over 24 as a decimal, 0.375. This would be negative 0.375. Okay? It's a negative 4. Would I still round that to negative 0.4? So the argument of why they ask you to round is because person A might have chose 4 as the x value for the maximum. Person B might have chose 5. Person C might have chose 6, right? Do you guys agree that your maximum here between the asymptotes is going to be kind of in that box? So So the rounding says if student A, student B, student C kind of chose maybe different X values to input because they visually thought that maybe the maximum happened somewhere different than what their friend or peer saw, that they would still vote because of the rounding end up the same result. Okay? So that's why they do that. I'm not going to ask you that. Obviously, you've seen on the practice test so far that is not a question I'm interested in. I do think you should be able to do that and understand that range. Really, the only way that we can find range for the most part, especially with these more complex functions, is to evaluate. Okay. Now, the next part of this, we would union this, and I get to my asymptote, right? So my horizontal asymptote is 0, and I'll go to infinity. I do not include 0 because it's an asymptote, right? I never get to it. Get really close to it, though. So that's what they're looking for on number 19. Again, I wish, for your sake, that they would, because you see it in other questions, that they would just kind of autofill the parentheses and bracket for you so that you know that that's got to be included. A lot of people come to me and they've got negative 0.4, but they got a parenthesis here, okay? They want you to include it. Is it okay? Another thing that I'm not a big fan of this question, because let's say that if we have, like, between our asymptotes here, maybe instead of this middle region being there, maybe that middle region is like that. That makes sense? Okay? And now I get, so I want to find this minimum point here. Let's say I evaluate that thing, and it gave me like 0.31. Go on. Cursor down home. There we go. So we got like 0.31, and it asks me to round that to the nearest tenth place. It's 0.3 now, right? Well, is 0.3 a range value? No, it'd be below that curve, right? I have problems with that. I don't like that type of kind of analysis. I'm more interested in having precise, exact values, solutions that are meaningful to us. I don't think putting 0.3 here would be meaningful to us. Does that make sense? Okay. But in regards to them asking us to kind of practice this concept of understanding range domain, it's really the only way that they can do it, and ask for us all to be graded, I guess, in kind of the same way. So this one here is the same thing. When we go through and kind of factor the bottom can be what, x plus 2, x minus 1. Top is going to be 2, x minus 2. And I do want to factor the top like that, okay, even though it's already linear. I would like to factor that 2 out to make sure I just don't have any holes. Okay? So I don't have any holes. I got vertical asymptotes at -2, +1, right? I'm going to do the denominator, so that's where you're seeing these two asymptotes. If I set the numerator equal to 0, you get a x-intercept at 2, correct? So that's what we're seeing over here. We get an x-intercept at 2. Compare the leading degrees. My leading degrees are, the denominator is bigger, so my horizontal asymptote is going to be y equals 0. Okay? And my y-intercept is going to be -4 divided by -2, right? Which is positive. Okay? So all that stuff is consistent with what we've been doing. I don't know why I wanted to erase that, but oh well. Now the question is, what's the range? Well, again, going from the bottom up, I go from -infinity. Now, am I going to close this off at 0, or do I go above 0? You go above 0, right? Okay. So I can't put 0 there. We go above it. Okay. I want to know how far above we go. When we have graphs like this, guys, that actually do intersect your x-axis, or sorry, not your x-axis, but your asymptote. Let me zoom in on this real quick. Maybe. All right, so what really happens, if we have a better scale here, this graph is going to come up. It has like a little bump up here, and then it gets sucked back down. Does that make sense? You can kind of see that bump here. More white region here, more white negative space here than there is over here, right? Okay. So we do have a little bit of a rise there, and then we get stuff back down. That understanding in regards to what our end behavior does and what our asymptote does, as that gets really, really big, kind of makes you understand, hopefully, that when I want to evaluate to figure out my range here, I don't want to use a number like 6 or 7 or 8 or 9. Okay. I want a value. I want to choose a value to evaluate that is around maybe these two. Does that make sense? That's where it looks like my largest gap between my red curve and my asymptote is. And that would then give me my highest Y value. Does that make sense? All right, so I would maybe evaluate at, so this is 1, 2, 3, or 4. Evaluate at 3 or 4. And when I do that, it's going to give me the Y value that I'm interested for my range. Is that okay? Does that make sense? Okay. And the idea of rounding then would tell me that if I use 3, I'm going to round to the same 10th place that somebody that used 4 would round to. Okay. Or maybe even the same 10th place that somebody would have rounded using 5. Okay. So that's the reason they're asking around. And again, I think it's kind of a fuzzy kind of question, but that's the concept. And they would want you to include that Y value then on your range. Does that help with those questions? Okay. So if you got through those, the next series of questions are talking about location of holes and slant asymptotes. Okay, so I want to do a couple examples of those today, and that should then wrap up pretty much everything I want to talk about in this chapter. First one is, let's go R of X equals X squared plus 3X minus 10. And we'll put that over, so X plus 1. X minus 3. And X plus 5. All right, so the task is, again, like all other rational functions, look for, now, you can have multiple holes. You can have multiple factors canceling out. So we're going to ask for that location. And remember another way of saying that? Okay, you might get to a calculus class and let's keep talking about with discontinuity stuff. Okay, well, it's just the kind of the mathematical, the more educated, more academic word for a hole. Together with holes, we usually look for vertical asymptotes. They kind of intertwine with one another. Then we're going to look for our horizontal asymptotes. If we don't have a horizontal asymptote, we'll have a slant or a oblique one. Then we look for whether we cross that, right? And then we do x-intercepts and y-intercepts. And if you've worked on that practice test that I gave you, this is kind of what I'm asking, right? I don't ask you to graph. I don't want you to waste time during class graphing those things. Because my feeling is if either you're going to be your third year of algebra, you should be able to graph things. If you can't, then it's your third year of algebra, you should be able to grab a calculator, grab a GeoGebra or Desmos and type those things in and get the visual, right? Okay. This is the important stuff that we're going to be interested in regards to those graphs, okay? And then this is also the important stuff. So these things are, a lot of rational functions have like real life applications. So intercepts and asymptotes and things like that would have a purpose to those real life applications. Okay, one application, if you were to read through the rest of the PowerPoint, is like resistance and electrical current. And the x-intercepts and that kind of stuff are key ideas or key concepts that electricians would be looking for in regards to that resistance idea. So we're very, this set of information here gives us some real nice information in regards to applying this stuff to real world things, okay? So, again, what we always like to do with this stuff is factor, right? Number one thing, factor every single part. So here all I've got to do is factor the top, right? So it gives me x plus 5, x minus 2. Bottom was already factored for us. Okay? What do you recognize there when we factor the top and factor the bottom? Common factor, right? Okay? X plus 5 over x plus 5. That's a common factor. When we look at them compared to one another through division, you get us 1, right? So they don't really impact the graph at all. Whatever x is, that's a factor of 1. Okay? So in regards to our final graph, what we start with, that blue function, compared then to this function, should be identical. 100, or let's say it this way, 99.9999999% identical. Okay? However, what I wrote over here is not exactly the same thing as this. Does that make sense? Okay? Because there was a factor here that we canceled out. All right? That factor in the original, if I were to choose x to be -5, and I evaluate r of x at -5, you're going to get 0 on the top, aren't you? You get 0 on the bottom, aren't you? 0 divided by 0, even though it's the same value divided by the same value. Now, all through mathematics, it's been taught, divide something by itself and you get 1, right? Except for the division by 0 precedent is more important. Even though you're dividing 0 by 0, you're still never allowed to divide by 0. Does that make sense? So 0 divided by 0 still is called an indeterminate value. Okay? That's a problem. Okay? So when we cancel our terms, x plus 5 over x plus 5, that gives us the location of a hole. Okay? It does not give us an asymptote anymore. It gives us a hole. So we set x plus 5 equals 0, and we solve. And it gives me an x value of -5 for the hole. Okay? Now, the x value of -5 is awesome, but there's an infinite number of y values when I go over to x equals -5 on my x-axis, right? Infinite number of y values to pair up with that. I'm looking for the one y value that on my curve that there's going to be a hole. Does that make sense? Okay? So kind of the idea is right now, let's say that my curve is maybe doing, I think it does something like this. I've gone over to -5. I know at -5, there should be a hole somewhere on my curve here. Does that make sense? We're now going to try to locate the y value for that hole. Okay? So how do I do that? I just substitute. To find y values, you substitute your x values. So think about where you're going to substitute. Hopefully, if you make a mistake, the result that you get leads you to understand that you made a mistake. If I want to substitute back in to find the y value, substitute in here. Substitute in the blue one or this red one here. What do you end up with? 0 divided by 0. Is that legal? No. Okay? So that should tell you you don't want to substitute there. Okay? You want to substitute in the reduced version. The reduced version is not going to have that factor of x plus 5 in it, right? So it's not going to give me that factor of 0 on the top and the 0 on the bottom. So plug -5 in over here. I'll plug -5 in over here. I get -7 up top. And I get, what, -4 times -8, right? So 32. Get -7 32nds for the y value of that hole. Okay? And you would want to do that for however many factors that you have that cancel. Okay? Now, what's nice about this is that everything else that we do, guys, can be interpreted from the reduced version. Okay? Or you can analyze your vertical asymptotes, your slant asymptotes, whether you cross it, your x-intercept, y-intercept, all that stuff from your from your reduced function. Okay. So if I find vertical asymptotes, the reduced function is going to be my vertical asymptotes are where? X equals -1 and x equals 3, right? Okay. The horizontal asymptote or the slant asymptote, and whether you cross it or not, you can look at either R of x, the original, or R of x, the reduced. Okay? Let me call this, just so I can talk about it easier, let's call this one R prime x. Actually, that's stupid. Let's just call it W of x. I won't call R prime of x because the next you're going to find out that R prime is a derivative. So that's just stupid notation on my part. So W of x, okay? So R of x, W of x, same function. W of x is the reduced one, okay? If I want to figure out the slant asymptote or the horizontal asymptote, whichever one I might have, I can either come back up to the original and compare the leading degrees, right? R of x, if I compare the leading degrees, it would be x squared up top over what on the bottom? X cubed, what's going to happen? What's it going to reduce to? 1 over x. Come over to W of x. What's the leading degree up there? X, what's the bottom? X squared, what's that going to reduce to? 1 over x, right? Because when I canceled that, that was a factor of just 1, right? So whether you look at the original R of x or you look at W of x, it doesn't matter. You need the same horizontal asymptote. Where's my horizontal asymptote here? Y equals what? Y equals 0. When x gets, I'm left with an x in my reduced version of my, or reduced comparison of my leading terms. I plug x in, x gets really, really big. I get 1 divided by a really, really big number. Gives me 0. Okay. Now the question is, do I cross it? Okay. What equation would you guys rather? So let's do it both ways. And then I'll let you kind of make the argument on which one you would want to solve. If I took, see if I cross my horizontal asymptote is 0. Set my function, I'll set my reduced function, x minus 2 equal to that, x plus 1, x minus 3. If I want to solve that, what would I do first? Multiply both sides by that LCD, right? Okay, if you want to look at this as a proportion, you cross multiply. Okay? And that thing's going to get wiped away. And you're left with what? X equals 2. So you're left with something that makes sense. Okay, you're left with a solution. So you cross that x equals 2. Now, let's say I took the blue one. Took the blue one, which would have been 0 is equal to, it was x plus 5, x minus 2 over x plus 1, x plus 2, x minus 3, x plus 5. And I see it if my original function crosses that horizontal asymptote. Again, cross multiply or multiply by the LCD. Doesn't this thing go away? Make sense? Now what are you left with? X equals -5 and x equals 2, right? So if you do this, it's not, this was correct. That was a real solution. But from what we've already found, can x equal -5? No. There's a hole there, right? At an x value of -5, you have a hole. You do not have any point on that curve with an ordered pair starting with -5. Okay? So you would have to have that understanding that even though that's presented when I do that algebra, what we've already done shows that it's really not a solution here. Does that make sense? So what to make it, hopefully it draws your attention to, isn't it easier to set the reduced version of your function equal to 0 to find whether you cross the horizontal asymptote or not? Okay? Because then you don't have to kind of work backwards and think about what you already found out and all that kind of stuff. Okay? So set the reduced version equal to your horizontal asymptote to see if you cross it. Be intelligent. What's y equals 0? What's that called again? X-axis. If we just say we crossed it at 2, when you cross the x-axis, what's another word for that? X-intercept. don't have to do that math again, right? People that are blind to the math and just want to be arithmetic and do the algebra are going to go through and they're going to set up the exact same equation again, and they're going to solve it the exact same way again. They'll get the right answer, but they've wasted their time. Okay? Y-intercept, okay? Here's another thing to kind of be thoughtful of. I'm going to go through and find the y-intercept like we always have by looking at the constant terms of the two polynomials, right? The constant term on the top is -10, correct? Constant term on the bottom will be last times last times last. So 1 times -3 times 5 will give me -15, right? What's that reduced to? 2/3. What did you divide out of both those? 5, right? Where'd that 5 come from? It was that common factor, right? Okay? If I reduce that common factor, and I just look at this, and compare the constant terms there, is it -2 over -3? Is it still 2/3? Okay, so that hopefully that shows you that your y-intercept can be found using either of those things. If you use the unreduced versus you use the original one, you're going to have to factor something out. You're going to have to reduce your y-intercept as fraction. Is that all right, everyone? All right, so I want to show you the comparison here of these graphs. Okay, so if I start with what we were interested with x squared plus 3x minus 10, and we'll divide that by x plus 1, x minus 3, x plus 5. Okay, we get that curve. Okay? Now, if I were to graph the reduced version, which would have been, what was it, x minus 2 over x plus 1, x minus 3. Would you agree that the red one and the green one overlay each other? So that's kind of the idea that I said the original and the reduced are 99.99999% the same. Okay? And this is where they kind of come up to be different. If and I want you to understand that these two things are different. Okay? Because of the reason of evaluation. If I were to evaluate G at -5, I get something back, right? Now, that number that we just got back should make sense to you. Didn't we find that a minute ago? Okay? Of the location of our hole, right? If I evaluate the original function at -5, it gets division by 0. It doesn't know what to do. It doesn't find, right? Okay? So, even though these two graphs are very, very similar, infinite number of points in common, they have one point that they do not share. That one point that they do not share would be located at -5, comma, -7, 30 seconds. Come on, there we go. And anything that you use graphically, CI83, 84, GeoGebra, whatever, decimal, is not going to put that hole in there. Okay? It's just something we have to do manually. We have to understand the reason it's there is because of that factor of 5, x plus 5 that we have to cancel out. Is that okay with everybody? Okay. Let's see here. Any questions on holes? All right, so the next 13 minutes, we should be able to wrap up this chapter. I want to talk about an example in which we get the comparison of leading degrees to be the one situation that we haven't talked about yet. If I have R of x, it should be x squared minus 4x minus 5 over x minus 3. This is different than anything we've done so far because the leading degrees, the numerator's leading degree is now larger than the denominator's, right? They've either been the same or the denominator has been bigger. Okay? This changes things. Okay? It does not change anything except for the horizontal and slant asymptote aspect of things. So when I go through and ask whether we have holes, what our vertical asymptotes are, horizontal, slant, sometimes, like I said, called oblique asymptote. That's what this comparison of leading terms is going to change for our problems. But we're still going to ask whether we cross. We're still going to look for x-intercepts and y-intercepts. And we should be able to find all those things pretty easily. Okay? But back to the top is me x minus 5, x plus 1, right? Bottom is x minus 3. Do I have any holes? No holes. Okay? Vertical asymptote. Do I have any of those? X equals 3. I'm going to come down here to x-intercepts real quick. X-intercepts. When the numerator is equal to 0, right? So 5, 0, negative 1, 0, right? Y-intercept. 0, 5, 3. See how fast we should be able to find all that information? So the only algebra is the factoring. Once we've got it factored, just recognition. Now there's algebra involved in our asymptote here. Okay, our slant asymptote or oblique. Here's the thing: if it's oblique, they're going to use the word oblique for things that are nonlinear. Okay, but at the same time, they can use the word oblique for something that is linear. Okay, it's kind of like I can call a trinomial, or I can call it polynomial, right? Okay, I call a binomial, or I can call it polynomial, right? Does that make sense? So something that is, you hear me say all the time, things that are linear, okay, they are still curves, they just lack curviness, right? You've heard me say that? Okay, we can still consider lines as curves, they're just better classified as lines. So you're going to see these two words. Slant is the indication that it's going to be a line. Oblique is the indication that's going to be parabolic, cubic, quartic, whatever. Okay. So this is the idea. If I was going to compare the leading terms, x squared over x, cancels out, leaves me x over 1, right? Okay. In behavior, called EB, says what happens to your y values as x goes to infinity. As x goes to infinity right here, what would y go to? Y would also go to infinity. As x goes to negative infinity, what's y going to go to? Negative infinity. So if x goes to positive or negative infinity, y does the same thing. Okay, so that's something different than what we talked about, right? Because usually we've gone to 0 or we've gone to some rational value, okay, for our end behavior. Now we're going to infinity. So we have to analyze it because we want to know, okay, we do go to infinity, but how fast do we do it? Do we go slow? Does it happen real quick? That kind of thing. And the way we determine that is we actually do the division that is being stated in the original problem. And I would just, I mean, you can do synthetic division, but synthetic division right now, the way we set it up, is that it only allows you to divide by linear factors, right? So sometimes it might be an x squared on the bottom, or x to the fourth, or x to the fifth on the bottom, or whatever. So this long division process is kind of the route that I would hopefully convince you to use. When we're doing long division, we're looking for what number do I put here, or what value do I put here, so that when I multiply by x minus 3, I get this first term in my dividend. Okay? So what am I going to put here so I multiply by x to get x squared? X, right? I'm going to do that multiplication then. Gives me x squared minus 3x. Okay? If you remember doing long division, you just subtract everything, right? I like to add. I'm going to multiply everything by a negative and then add straight down. So those go away. Gives me negative 4 plus 3, which would be -1, right? Bring down my -3 that I haven't used. I guess that's a 5, isn't it? All right. Bring that 5. To be honest with you, it doesn't matter. 5 has no impact on this. So now what do I put here? So when I multiply by x, I get this -x. -1. Multiply by x minus 3, so we get -x. Plus 3. I'm going to negate everything and add it straight down, so it gives me -8. Okay? And now I stop because that's my remainder, right? I always stop when my variable term here is 1 less degree than my divisor. So x to the 0 is 1 less degree than x to the first, right? So I would write this as my quotient x minus 1 plus my remainder of -8 over my divisor x minus 3, right? Okay. So that is what is really happening here when I take that and do that division. Okay. But remember, what we're interested in for a slant asymptote or horizontal asymptote is in the behavior, right? When x gets really, 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 really big. Think about when x is $1 million. You got $1 million, take $3 away from it. You still basically have $1 million. Yeah. So it's -8 divided by $1 million. Pretty close to 0, right? If I had $1 billion, take $3 away from it, or still got $1 billion, right? Okay. Divide -8 by $1 billion, it's pretty close to 0, right? So as x gets bigger and bigger and bigger, is this thing negligible? Doesn't really matter. All right, and that's what I said earlier when this is a 3. Right? It would just change that numerator, but it's negligible. It doesn't really matter. Okay. The only thing that's really impacting my end behavior is x minus 1. That's my equation of my slant asymptote. Okay. Your quotient, with disregard to your remainder, your quotient of that division is your slant asymptote. Okay. So you can see, we have to graph that then, right? Graphing a horizontal asymptote pretty easy. Okay. Graphing an oblique asymptote, if it's linear, not too bad. If it's quadratic, not too bad. If it's cubic, quartic, quintic, that's all back to the start of chapter 3, right? So you start to see how maybe sometimes, depending on what our oblique asymptote looks like, this might be a task in regards to graphing it. Okay. I'm going to come over to GeoGebra and just put this stuff in. If we looked at what was it, x squared minus, or was it plus 3x minus 10? Divided by x minus 3, is that right? No, x man. Is it the one before? Minus 4x. 5. All right, so this is what that graph looks like. Okay, we still have a vertical asymptote at x equals 3, right? The vertical asymptote. Okay. Now, if I graph y equals x minus 1, would you agree that my blue curve follows that behavior as we move further and further to the right, and then further and further to the left? Like that? Okay. We can still ask the question, do we cross it? Okay. We simply take the original x squared minus 4x minus 5 over x minus 3 and say, do we cross x minus 1? Again, multiply by the LCD of x minus 3, right? You put x minus 3 over here. All right, it's going to save you a little bit of time when we FOIL that out. So it's going to be x squared minus 4x plus 3, right? X squared minus 4x plus 3. What happens to your x squared? They cancel, right? What happens to your negative 4x's? They cancel. You're left with negative 5 equals 3. True or false? False. Do I cross it? No. Okay. Just want to show you real quick what happens if we have something like this. Okay? x squared minus 16 over x squared minus 1. If I were to divide the leading terms, you're left with x squared, right? Make sense? So my end behavior is going to be some x squared type end behavior. So if I did the long division of x to the 4th minus 16 over x squared minus 1, I would end up with that blue x squared plus x plus 1. That's what that comes out to as my quotient. Okay, there's a remainder. I think it's like a remainder of like 15 or something like that. But there is some type of remainder, but it's negligible. Look at this green curve. Okay, do you see as it moves to the right, it starts to increase to infinity? Okay, but it's increasing to infinity following the behavior of that asymptote, right? Does that make sense to everybody? Okay. Now I've kind of adjusted my y-axis here a little bit, maybe made too much to see. That's kind of what that graph would look like, that green. Okay. But a portion of that is following that asymptote. These would be the vertical asymptotes for that thing, x plus 1, x minus 1. So you still have, just like what we've been doing with horizontal asymptotes and vertical asymptotes, does that still break my plane up into regions? And we would go through and try to evaluate at certain points in those regions and see what our graph looks like. Okay? We're not going to do too much with oblique, x squared, x to the 4th. Actually, we're not doing anything other than what I just talked about with you. I want you to know that when we do slant asymptotes, there is an extension to that. You can do more with them if you need to, or if you want to. Okay. Test tomorrow. I sent an email yesterday with the key to that practice test. My hopes are that you spend some time on that. Okay. Spend more than an hour, 2 hours on that. Spend some effort on it. Okay. Then what I would suggest doing, once you feel comfortable with everything, start from scratch and see if you can take that test in 45 minutes. Okay, to give you an idea of how well prepared you are, right?